Okay, so let's consider a simple regulator given by this differential equation. Forget about feedback, it's got nothing to do with feedback now, it's just a regulator. In other words, it's a homogeneous differential equation. X dot is equal to AX. And the question that I'd like to answer is what happens to the response of this system as time goes to infinity. Now, of course, it being a regulator, the only way that it can have a response is if there's somehow the initial condition. So it starts off from a non-zero initial condition. And then there will be some dynamics due to the homogeneous solution. But where does that response go to as time goes to infinity? That is the question that I need to answer. And I need an answer to this question in order to carry on with my observer calculation that I've just now interrupted. So we know that for a system like this, the solution to the homogeneous equation is actually through the state transition matrix. Remember that I'm limiting myself to a time invariant system. In other words, my A matrix here has got constant coefficients. And then I know if I've got a time invariant system, the state transition matrix is simply the matrix exponential of the A matrix times t. So at any point in time t in the future, I can calculate the state vector, xt on the left-hand side, by pre-multiplying the initial state vector at time 0 by the state transition matrix. Because it's time invariant, the state transition matrix only has one argument, namely the time t at which I want to calculate the response. So this is already then the solution, the solution of the homogeneous differential equation, which was my state equation. And on the far right here, I've simply written x evaluated at time 0, in other words, the initial state vector, as x sub 0. Okay, so I'd like to know what happened. Can I predict anything about this xt? And perhaps you have already some idea of what it should be, but let's see what the mathematics shows us. Okay, I've already now stated this question in words, but here's the mathematical statement of the question. Now, to answer this, let's consider the eigenvalue problem where lambda I, all of them, all k, let's say our matrix A is of order k, so it's a k by k matrix. So I've got k eigenvalues, and they are indicated as lambda 1, lambda 2, etc., lambda I up to I equal to k. And let's say that the corresponding eigenvectors are beta I. So beta is a vector of the same length as the state vector x, and it's the eigenvectors of the A matrix. Then I can write this equation. For any one of those eigenvalues, I can write this equation, because this equation is really the statement of the eigenvalue problem. And we know that if I state the eigenvalue problem in general terms and I solve it so that I determine the eigenvectors and then I determine the corresponding I solve the eigenvalue problem to determine the eigenvalues, and then I also solve for the corresponding eigenvectors, I can surely substitute that back into the eigenvalue statement and it should satisfy it. So that is really what this equation says. It's the matrix A times the eigenvector, the ith eigenvector is equal to the eigenvector, the ith eigenvector multiplied by the ith eigenvalue. Okay, everybody happy with that? Now, I can state this for any one of the k eigenvalues. Sorry, I need to, Friedland uses k for the order of A, I've used n, a small n. So if I now put all small n eigenvectors in a matrix, which I call P, in such a way that each column of this matrix P is an eigenvector. This matrix P is often referred to as the modal matrix, especially in the vibrations world, they will refer to this as the modal matrix. Now, if I do this, and then I insert all the eigenvalues in a diagonal matrix, which I label as capital lambda. So the lambda i's are the diagonal elements of this capital lambda, and all the off-diagonal elements are 0. And the sequence in which the lambdas appear on the diagonal of lambda is the same sequence in which the vectors, the eigenvectors, appears in the modal matrix P. If I do that, then I can rewrite this equation, which is just for a single eigen value. And by the way, if you look at this equation, left-hand side is a column vector, right? Because I've got a column vector beta pre-multiplied by the matrix A. So this product gives me a column vector again. And on the right-hand side, I've got a column vector that I multiply with a scalar. So that's also a column vector. So, but if I then do this generation of the P matrix and the capital lambda matrix, it allows me to rewrite this equation that was just for one eigenvalue for all eigenvalues simultaneously in this form. And now it may look funny because it seems if I've turned around the sequence on the right-hand side. But remember, lambda is in any case a scalar. So if I just look at the scalar equation, I could have written the right-hand side as beta I, the vector, multiplied by lambda I also. That would have been correct. But of course, down here, I cannot swap them around, because what this means is that here I've got the matrix A. And if I just look at, when I do this matrix multiplication, the first column of P multiplied by A would be like A beta 1. And the second column of P multiplied by A would be like A beta 2. On the right-hand side, the first column of capital lambda multiplied by P would be the same as lambda 1 times beta 1. So clearly this equation is exactly the same. Well, it's not exactly the same. It's the summary of this equation where I now have included all eigenvalues into that. Is everybody happy with this? Okay, now if I now do a next trick and I post-multiply this equation on both sides of the equal sign by the inverse of the modal matrix P, I get what is called the modal decomposition of the matrix A. I've established the identity that says that my A matrix can be written as the modal matrix post-multiplied by the eigenvalue diagonal matrix, whatever you want to call it. I'm not sure whether it's got a name, but let's call it capital lambda as the eigenvalue diagonal matrix, post-multiplied by the inverse of the modal matrix. Now, this modal decomposition of the matrix A is used for various purposes in various sciences. So you will probably meet this again sometime in your life. But for our purposes, I'm repeating it on my next slide, I'd like to now look at the matrix exponential. The matrix exponential is defined in equation 3.4 of Friedland in terms of the Taylor series expansion. That's the very basic way in which the matrix exponential is defined. And of course, at the time when we first saw this, we agreed that it's not very easy to calculate the matrix exponential in this way, but yes, this is how it's defined. Now, if I look at this definition and I now substitute the modal decomposition of A into this equation, something interesting happens. Okay, I'm writing the identity matrix on the far left of equation 3.4 just as P times P minus 1. P times its inverse. Remember that the matrix P is of the same order as I and the same order as A, right? So P times its inverse will give me an identity matrix. But then this term becomes P lambda P minus 1 times T. This term becomes P lambda P to the minus 1 times P lambda P to the minus 1. So the P minus 1 and P in the middle will cancel one another, and I'll be left with P lambda squared P to the minus 1. And then, of course, that needs to be multiplied by T squared over 2. And exactly the same for the third and the fourth and all the different powers of A, all the P minus 1 P's in the middle will cancel. And I will every time have just P times lambda to the power of whatever the term would be, 3 or 4 or 5, times P minus 1. This then means that I can factor out the p to the front and the p minus 1 to the back. Remember, the t's are just scalars, so I can swap around the t with the p minus 1. It's no problem because t is a scalar, and t squared over 2 is a scalar, and t to the third over 3 faculty is also a scalar. So I can swap them around, and so I end up with this expression. And this expression I can then write as P times a diagonal matrix, and I'll get back to that in a moment, times P minus 1, where everything in the square bracket is a diagonal matrix. And why? Well, the whole matrix character of this is the eigenvalues. So if I take the square of a diagonal matrix, I'll simply have the diagonal matrix of which the elements are the square of the original elements. And the diagonal matrix to the power of 3 will simply be the original diagonal matrix elements on the diagonal raised to the power of 3. And because of that, I can write this diagonal matrix as the diagonal of e to the lambda I t. And so I've just repeated that at the top of the slide. So if I now want to look at before I get there, let's now also consider that the eigenvalues of our A matrix, the lambda i's, in general can be complex. So if they are complex, e to the lambda I t will be e to the sigma I plus I omega I times t, where sigma I is the real part and omega I is the imaginary part of the complex eigenvalue lambda I. And through the product rule of exponentiation, this can then be written as e to the power of sigma I t times e to the power of I omega I t. Okay, now can you tell me something about this second factor that we have in this factor of 2 exponentials here? Anybody that will like to comment on e to the I omega I t? Yes, yeah. Yes. So, and its amplitude? It's 1. So it means that this is a unit vector. It's a rotating unit vector in the complex plane, which is why you say it's sinusoidal. It's not wrong to say that, but it's perhaps the most accurate to say this is a unit vector that rotates with the angular velocity of omega I. So this can never be, in magnitude, can never be smaller or larger than 1. It's just 1. The magnitude of this is 1. This guy on the left-hand side, though, we know that if sigma I is larger than 1, this guy will blow up as t goes to infinity. On the other hand, if sigma I is negative, this guy will get smaller and smaller and smaller as time goes to infinity. So keep this in the back of your mind. If we now move back, I can, because of this, then claim that the limit of e to the I omega t, if I just look at this single eigenvalue, the limit of e to the lambda I t as t goes to infinity is the limit of this, which means that it's 0 if sigma I is smaller than 0. If sigma I is negative, this limit is 0. And now if we go back to our original equation, the point was that we'd like to determine the limit of the matrix exponential as t goes to infinity. But since the matrix exponential we've shown is simply the P matrix, now remember the P matrix is a matrix of constant numerical values. It's the eigenvalues of the A matrix. So it's not time varying values. And of course, likewise is P minus 1. So as t goes to infinity, whatever happens here is purely determined by what happens inside this diagonal matrix. But for each element in this diagonal matrix, we have shown that the limit as t goes to infinity is 0, provided that the corresponding real part of the eigenvalue is negative, which, by the way, we've seen before is also the requirement for the system to be stable. So the conclusion that we then see is that the matrix exponential in the limit is a 0 matrix if the system is stable. And so this probably confirms what you've intuitively thought, that when I ask the question, what happens with a homogeneous solution as time goes to infinity? The answer, mathematically we've shown. The answer is, well, if the system is unstable, it blows up, it goes to infinity. But if the system is stable, if all the sigma i's are negative, then the matrix exponential is a zero matrix. So that means then, if we calculate the state variable, which is now the product of the matrix exponential with the initial state, we see that as time goes to infinity, our state vector goes to zero, because we are pre-multiplying our initial condition with a zero matrix. So this you may have you may have had this in the back of your mind. This is what's going to happen, but here we've now mathematically proven this. Okay, and I think this is the end of this. Well, okay, so this just put this equation into limits, but it's basically what I've already said. Everybody happy with this? Okay, so let me just stop this recording.